we're going to enter the second part of calculus. So the first part deals with derivatives. The second part is going to deal with something called integrals. So to help us understand why and how, we're going to start with just this problem. We're going to find the area under a curve using ideas of calculus. Okay? So the problem is I have this function right here, which I'm going to call f of x, and I want to find the area underneath this curve that's bounded by the x-axis, so like only dealing from the x-axis and up, between x equals 2 and x equals 10. So this part right here that I am denoting with the green lines. So if I had an equation to work with, I could try to do this a little more calculus-y, right? Because I can show you how to find an integral. But the purpose right now is just to show you what an integral is, what does it mean, and then I can show you some of the steps. Because I want to make sure you have a good fundamental understanding of what's going on, and then we can worry about the numbers later. Okay? So if my goal is to find the area underneath a curve, I need to find area, so I need to find area formulas. There are lots of them. I could use triangles, I could use rectangles, I could use parallelograms, I could use squares, I could use hexagons, pentagons, all the different shapes, right? They all have some sort of formula. But let's try to keep it simple. So I'm just going to deal with the rectangle. Because I know a rectangle to find the area of a rectangle, the area is equal to base times the height. So if I can identify the base and if I can identify the height, then I can just find the area right there. But we run into a little bit of an issue right now because I can't really, like, this is not a rectangle, right? If I try to make this a rectangle, that means I need to have two sets of parallel lines and they have all the angles here are right angles. But if I visualize it this way, right, here's my rectangle. But it's not a good estimate because this entire part is left out of the area calculation, right? And if I try to adjust, then I can make it this way and I go straight down, but then I have, again, an overcalculation because this part that's in the pink would be counted even though it shouldn't be. So we have a little bit of a dilemma. Oops. That's fine. Because what we can try to do now is we know that we want to find rectangles, and I know it has to be between 2 and 10, so kind of estimating that's what the picture would kind of look like. And I know I want to use rectangles because rectangles are super nice. However, I can't just make one giant rectangle because it doesn't work. What I can do, though, is try to break this up into smaller and smaller rectangles, right? So if I can find the area, well, actually, my goal is to do this. Break shape up into small rectangles and add them up. Sorry about that. I was making a lasagna. So, add up all of those rectangles. Okay. So if I do this, it makes sense because if I just try and do the more rectangles I can break this up to, the better of an estimate I can get. Because if I just break it up into, I don't know, if I break it up into two, I would have one rectangle, let's say this way, and then to be consistent, we'll always go left to right. We don't have to, but just to be consistent. So this part right here could be my estimate for the area. However, again, it's not a good estimate because parts are being left out. So what I'm going to do instead is break it up into more rectangles, right? So let's say I did one for every single line right here. Right, go straight across and down, straight across and down, straight across and down, and right, as you see, I am making more and more rectangles. So automatically my guess is going to be better. However, I'm still missing some spots here, 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 here. You know, as I make my way up, there are little spots that are still missing. So even then, I still have to accept this as some sort of estimate because there's still those missing spots, right? So what mathematicians decided to do is this. Um, Rather than beat our heads against the wall trying to figure out what's the right amount of rectangles to take, they decided, okay, well, let's just generalize a pattern and we'll go from there. So here's what I can do. I can just accept it and think about this conceptually, all right? If I break this up into n amount of triangles, or rectangles, geez, wrong shape, right? So let's say it's this right here and this over here. And actually, I'm going to clean this image up a little bit because this is going to be too much. All right. And don't worry about the specifics right now. I just want you to get the idea of what I'm trying to go for here. So if I make it this, 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 like from here to here, let's say this we're going to call delta x I. And each of these will have the same space between them. Ideally, that's what it should be, where they all have the same delta x sub I. Because if you remember, I think I said this once, so if you don't, that's fine. Delta x is just, the delta part just talks about change. So I can say that I have a rectangle. It'll have delta x as its base length, And if I go back to the image and I think about what the height would be, well, the height would be the distance from this point all the way up here, which we can just call f of x. And that's going to be true for every single one of these, starting from the bottom. Now we're here. Starting from the bottom, now the whole team is here. All right? So if I imagine that I'm taking this shape and I'm subdividing it into who knows how many rectangles, right? The height will be dependent on the actual x value that I give in. So f of x plus that delta x, right? To go from here to here, that's what the input is right here, okay? And I want to add all these up. So to represent that addition, mathematicians have a symbol called sigma. And that's to add up terms. Rather than write out every single one, if I have like a pattern, I can just use this right there. So let's talk about what the sigma has. A sigma has certain components. It's where am I starting, how many I have, and what exactly am I adding. Right? So right? So that's what the sigma notation is, and that's how you read it. Ideally, for the amount of triangles I have, or amount of rectangles I want to have as many rectangles as I possibly can, because the more rectangles I can divide that image into, the better my estimate will be. So, as a result, I want to have n be as many as possible to continually keep increasing. I am right now trying to set up a limit. Specifically, I want the limit as n goes to infinity. So I want to have infinitely many rectangles being added up. All right, and I'm going to start with just the first rectangle possible, right? So just I move over this itty bitty amount, and here's what I'm going to keep adding up. I'm going to keep adding up that area, and that area is found by the height based off the input times the length, or times the base, I guess I should say. So this represents the height, and this represents the base. So in this complicated looking way is just what we're trying to accomplish, right? I'm not going to ask you to go ahead and find it right now because you don't have enough information to even make a reasonable guess. And I can't ask you to break this up into infinitely many rectangles, then find the area that way, because that's going to take too much time. But I just want you to understand what that is. So another way that this could be expressed is right here. I want to find the integral from 2 to 10 of the function with respect to x. So if you notice, right, this delta x shows up right here. This f of x, the height, shows up right here. And what this is doing is this integral is just talking about a sum. It's another way to represent the same idea. In fact, it's actually representing this part right here. The limit of a sum is that integral right here that I'm about to box in. That's how we can say the same thing in two different ways, right? And in the next couple of days, we're going to focus a little bit on just making sure you know how to set this up, and if I give you a picture, how to find the area of that image. And if it's a nice shape, cool, we can do that. And if not, well, let's talk about different ways we can estimate it before we jump into this integral, which is what I have on this side. That is what an integral looks like. So it's a lot to take in. If you're a little confused, okay, that's fair. But if I go back to the original problem, right, and I think about what they're trying to do, what I want you to know is this. This question right here was asking you to find the integral 2 to 10. So notice how I take those numbers and I take the curve, whatever the function is, and I make sure I take the integral with respect to the variable that I'm trying to find it in. That's what this problem was trying to ask you. That's how you want to think about transforming it. Okay.